present from here.
Yeah, I'm worried. Okay, it's coming.
Okay,
Yeah, so I'll go full screen. Let's see. Yeah, it's not taking full screen. Let's see. Hmm. It's coming. It's happening. This one. All right. Okay. Hi everyone. Hope I'm audible to you guys, right? It's not audible. Okay. Right. Let me-
man.
Yeah, yeah, please. Is it fine? Better? You can't hear me? Now is it fine? You can hear? No? Is there a mic here or is it just for the? Acha, it's for both. Yeah, just increase the volume once. Not audible? Now, okay? Last. Is it fine? Okay, great. So, how was the previous session? I think it was very engaging, right? Everyone was talking. It was really good. So, all right. So, let me just give my introduction first. So, I am Riktim. I work in quantum hardware particularly. And today I'll be covering quantum random number generator. So, my colleagues are all CS people, but I am a physicist by training. So, my examples will be more physics oriented or more like practical oriented. Okay. So, by the way, can anyone tell me, do you know where quantum leave quantum? Let me say, do you know where random number generators are used? Or anyone can tell some use cases of where we see random number generators? Yeah, more? Your OTPs, those are very random, right? If someone gets any knowledge about the prediction of those OTPs, all our digital infrastructure is gone today, and everything is digital today. Even this call is being recorded digitally. So, getting pure random numbers is a very crucial knack we need today. All right. So in the random number generator class, first there are like two classifications that we should see. Like for example, software based and hardware based. So when we see software based things, those come in the class of pseudo random number generators, or which are algorithm based. But the problem with them is the numbers the generator, they will pass some tests, statistical test and everything, but they run by a seed. The moment you know the seed, you know the sequence. So that's the problem with pseudo random number generator, and they are deterministic in nature. The next class is true random number generators. So these are like actual hardware-based noisy devices. For example, someone is sitting in a laptop and they are like just pacing the space bar. So even that's a random number. Like they'll do it in a random sequence. It's not predefined. It's like he's sleeping and he's just, okay, one click, that's 1 0. After 5 minutes, another click, okay, this is one. Suppose something like that. And such things exist in our hardwares also. Even the desktops that we use, they have some form of classical or heat noise is coming out of that. Even we can probe those as also random numbers, right? So these are like, so the class of true random number generators are, they should not be deterministic. Now deterministic, what I mean is that you should not be able to predict when the zeros and ones are, right? And luckily in this class, quantum entities are very useful. Why they are useful? Because we talked about certain things today. Okay, like certain things are like quantum superposition, quantum entanglement, and someone was asking about superposition also. So superposition state is like, it's difficult to imagine, definitely, because all our vision or all our ideas are developed on the macro scale today, like whatever we can see. So we can see anything in, not, we cannot see in micrometers also. Micrometers is like you go 10 orders less than a meter. So we can see whatever we can see, our intuitions or our logic is developed on top of that. But quantum starts beyond that. Like you go further down. The moment you go further down, the things, like it seems illogical to us. Like how can the switch be on and off at the same time? We don't understand it because our logic is not derived from that. But that is not how nature works, right? So talking about quantum principles, we have something called a superposition. So superposition is like 0 and 1 simultaneously. That's a real state which exists. And on the course of the lectures, we'll see like how we can actually use those entities or how those entities are being designed at the first scale. Okay. Now, before we move on, it's important to just skim through like why are we learning this or why are we trying to understand QRNGs? Because they have a lot of useful applications today. And to say this, QRNGs are one of the most promising applications of quantum technologies today, because they save us from a lot of things. Like they can save us from financial frauds. They can help us with better predictive models in financial modeling, help with cryptography, any communication that we're trying to do. WhatsApp, for example, we can replace those numbers with actual truly random numbers from quantum sources. And the list goes on and goes on. But before we delve into this topic of why quantum, we should first appreciate like what is the need of quantum. So to understand that, we should look into the entropy and information theory first. So even I said like there are classical hardware also, like heat is a noise, electronics is a noise. Why then quantum? Like what was the need for getting into quantum? The answer is lies in the entropy. The entropy of those heat-based sources or thermal-based sources cannot be defined. And entropy is related to information. It's like the more random it is, the less information you get. Okay, that's like inversely proportional. So what people found out that with quantum entities, even though they are very unpredictable, their entropies can be defined. But with classical or these hardware-based noises, this entropy definition is very difficult to be defined. So we'll look into two important entropy parameters. There are a couple of more also, but these are more important. One is, first is Shannon entropy. So Shannon entropy measures the unpredictability in a random sequence. It will give you the average information that you can get out of a sequence. And this is the mathematical form. So can anyone guess what is the maximum it can take, maximum value? It's log n. So it's there in my slide, by the way, anyway. And yeah, so that's the maximum value it can take, and the minimum value it can take is 0, right? But then there is another entropy I'm defining, which is called as minimum entropy. Interestingly, what minimum entropy does, it gives you the measure of highest probability of guessing an outcome correctly. So now you see, by definition, minimum entropy will give you information about how much information any adversary can get out of your random sequence. And that is what we are trying to protect. Like we don't want our random numbers to be known by anyone, right? And to see the difference, how they both differ, like someone can say bluntly, okay, my system has an entropy of 0.9. If it does not define what the entropy is, it can be a real game changer. And if you can just take this thing to my screen, because there is an example here I want to show. Yeah, this is great. So let's see a very simple example of a fair coin, which is a 50-50 probability. So it has a 50-50 probability. The Shannon entropy is 1. The minimum entropy is 1. Guessing rate is 50%. That is the maximum very good case. But if it is a biased coin, which is 80-20 chances, see the Shannon entropy is 0.7. Minimum entropy is 0.3. Now, if the adversary would not have defined me what my entropy is, I was so happy, like 0.7. But 0.7 of Shannon entropy means that I have a guessing success rate of 80%. Like out of 100 chances, 80 times I'll be able to guess it correctly. So that's how entropy definitions are important in defining a random number sequence. And this is a graph to show, like if it is unbiased, both the values are very, very much same. Then as the bias increases, Shannon entropy comes down very slowly, but the helpful parameter is the minimum entropy. It will come down really fast. So whenever you see a QRNG, the first question you should ask is, what is the minimum entropy? Okay. Now, from the morning session, we have talked about a lot of things: quantum superposition, entanglement, measurement, and Heisenberg's uncertainty. I'll just spend 5 minutes on this. So, superposition is a state where a qubit can be simultaneously +1 or -1, or 0 and 1, both at the same time. And these are, by the way, physical states. Then there is something called as quantum entanglement, and this is something I do generate every day in the lab. So these are like very two twins. These are like exactly twins. So anything if you do to this guy knows immediately, and there is no information which is flowing out. Okay, and this has been proved also. Like there is some one concept in quantum called as non-locality. So local systems are like, for example, anything happening to that room you will not be aware of right now. Exactly right, because unless someone calls someone on that room or you go and see it, it's not known. The state is not known what is happening. So we call them as, so local is something which is around you, non-local is something which is not around you, which is outside your surveillance. Quantum entities are non-local in nature. What it means that if I generate an entangled pair, I keep one with me, the other I'm sending there, whatever happens to that guy, I will know immediately. And they are not sharing any info. No one is going and telling me. No one is coming and telling me that, okay, the state is one, you should be also one. Nothing is happening of that sort. So these are something very peculiar things which is very fundamental or very elementary in quantum world. Next is quantum measurement. Now, this bonds out from quantum superposition itself. Because the state can be simultaneously in 0 and 1, when it is measured, it can either be 0 or it can either be 1. Okay. And these are like not very intuitive things, but this is how the world actually works. The atoms, they actually work in this way. And the final is Heisenberg's uncertainty principle, which says that if you know the position of something very accurately, you don't know the speed of it traveling. But let's not delve more into that because that will bore the lecture. So, yeah. Now, like I was telling about, the classification of true random number generators can also be done in two classes. First is classical true random number generators and quantum true random number generators. So if it is a classical random number generator, it can be from a diode noise. For example, if there is some light, for example, this light, I can just note down its power fluctuations, and that also I can generate a sequence. If it is just some light which is emitting, I can, from the noise of that light, I can do some random sequence out of it. But that is not how quantum sources work. They will take either superposition as their fundamental thing, or they will take entanglement to generate. In the coming slides, we'll see how that exactly is done. The main thing to see here is the entropy bound. For classical true random number generators, the entropy bound is not definable. And that's why the market is so much like the QRNG market is so much promising, because they give you a better bound, they give you better unpredictability also. And definitely, because they have so many positives to them, they are well suited for high security applications. And this slide is a like an overview of how RNGs can be classified. Like starting from random number generators, first they will go into pseudo random number or true random number. When it comes to true, then it can be either classical based or it can be quantum based. Then if it is quantum based, then there are three classes. One is called as trusted, one is called as semi-self-tested, one is self-tested. Now what is this? Trusted means, for example, you have bought a QRNG from someone. They are not telling you, it's a hard IP of them. They are not telling you anything about that. So you are just trusting the vendor that whatever they have given is quantum to me. That is the trusted class of QRNGs. And you are believing them that whatever they have said they are doing is actually what they have done. Next is semi-self-tested, where the user gets some power of verifiability. They can actually check, okay, whatever they have said quantum, is it really quantum? I can check that. And finally, self-testing, where user gets complete power, complete thing they can actually check whether whatever the random sequence is generated is completely random or not. And these are the subclasses to that. How can it be done? But we can just skip that. Now, like I said about random number generators, there are different processes which has been explored on doing random number generators. Like it can be either photon based, photon is like light based. It can be either matter based, which can be spins of electrons that we can see. But to make it more interesting, let's see some of the processes. So I'll tell that light has polarization. So do you understand what is polarization? Anyone? You do, right? Okay. Yeah. So yeah. So light has lot of degrees of freedom. One is that. So we say that light is polarized. It means that either it is horizontally polarized or it is vertically polarized, which means that the exactly. It is either, like, for simplicity, it is either this way or it is this way. If it is this way, we call it vertically polarized. If it is this way, we call it horizontally polarized. To see it, so my screen guard has a special cover on it. So you can see whenever, like, you guys are straight to it, you can see my screen, right? But if I just tilt it, it's completely dark because it is not allowing any polarization which is out of line of sight to pass. And same for you also. Like, if I just rotate it slightly, you will not be able to see it. So that's how light is polarized. And that is something we use to generate random numbers also. How we will see it? First is there is a single photon source. So this photon source is responsible for generating either horizontally polarized light or vertically polarized light. Then I have a device which is called as a beam splitter. So this is a special entity. Imagine this as a black box. For example, this is the box. So if horizontally light is coming to it, it will straight away pass it. If it is vertically polarized, it will just reflect it. Okay. And this source is generating a superposition state, which was my initial state, if you remember. Where are the pen? Okay, it is here. So let me just draw it. So my state that I'm sending it is this superposition state I'm trying to send. Then I have a object which is called as a beam splitter. Like the name suggests, it is supposed to split a beam. Okay. So if it is horizontally polarized, it will go straight, and horizontally polarized, let me call this state as 1. And if it is vertically polarized, it will come this side, or it will get reflected. And I have two detectors over here. Let me call it as D1. Let me call it as D2. Now see, because this state is in a superposition, and we have learned that measurements can collapse the state in either of the bases. Either it can be 0 or it can be 1, any of the possible states. So this guy over here is acting like a measurement operator. So in the previous class, you have seen we were using some measurement gates, right? And we were trying to, like, it was something like this. There was a meter over here, and you were trying to drop in that, right? And you were seeing that the moment a single qubit was there in the 0 state, a Hadamard was put, and then there was a classical register over here. So the moment this thing was done, you have seen there are two probabilities which is forming up, which is of 0 and this is for 1, right? If you remember from the previous hands-on session, we're trying to do the same thing here. Now here, measurement, we have just dragged and dropped it, right? But physically what it is? Physically, this kind of devices are used. This is a measurement device, which is a beam splitter. What it is trying to do, it is trying to say, okay, if you are if you are horizontally polarized, just go straight away. If not, just reflect back. Sorry? No, unpolarized we cannot do. We have to prepare the light in a 0+1 state. So there are like different polarization. Okay, let me just tell that also. So first thing is, whenever we say something is unpolarized, light by itself is polarized. Unpolarized is our lack of information. We don't know how much it is. Okay, like the state is something unknown. I don't know what it is. But the moment I have knowledge of the state, we call it linearly polarized or circularly or diagonally polarized. So if it is just H or V, then it is linearly polarized. If it is H plus, okay, wait. If it is H plus V by root 2, and this can go plus and minus, it's called as diagonally polarized. If it is H plus minus iota V by root 2, it is circularly polarized. So if you have went to 3D movies, the goggles that you wear, they use circularly polarized phenomena. The films are meant to play around with circularly polarization. That's why you can see on the flat screen two different objects, front and back. Okay. So this is the state I'm interested in right now. Why? Because it can be equally 0 and 1 or H and V at the same time. And that randomness I want to harness on this guy. The moment I do that, I get a random sequence of zeros and one. As simple as that. And you see how this is different from any hardware based or classical sources. Because here I'm using quantum superposition as my result or my entity, actual entity to do this, to churn out this randomness. That's why quantum processes are simpler and also they promise a lot of advantage. The other thing is, which is a little different from the morning, you have heard about quantum entanglement a lot. You have learned the states, right? But how do we generate them in the lab? So this is a crystal, a special crystal. So when this crystal is excited by some photons, it creates two pairs out of it. Meaning one photon will go in, two photon will come out. Okay. So now, for example, this photon. Okay. Now suppose this photon had energy E, and there is one crystal over here, which is this part. The moment this photon enters into the crystal, it splits out into two parts, which has energy E by 2. And that's possible physically also, right? E goes in, E by 2, E by 2, two photons. And these photons are particularly entangled in nature, which means that any property which is found on this guy is maximally correlated with this guy also. And the state which comes out is 0, 0 plus 1, 1 by root 2. Which means that the moment you get 0 over this guy, you are certain that the other guy is also 0. If it is 1, the other guy is also 1. Which also means that, now see, in this entangled state, there is a very interesting thing to note, which is if it is 0, then it is the other particle is also 0. But the probability of this state and this state is again equal, which is similar to superposition, but in 2 dimensions now, with 2 qubits, right? Which means that the same property I can use again to generate my random numbers, but now 2 streams. I initially with that I just had 1 stream, but now I have 2 streams. One going randomly, the other is doing on its own. So these are called as photon-based QRNGs that we see. Okay. The next class is matter-based. So not all qubits are photon-based. Like superconducting qubits, they are not photon-based. They are matter-based. So the other class which can come in QRNGs, which is matter-based QRNGs. So in this, instead of sending photons, we send atoms. So in this example, we send cesium atoms from an oven, and basically it's the same thing. Then there is a inhomogeneous magnetic field to it. So what people initially predicted, and this is a very famous experiment in physics also called as Stern-Gerlach experiment. So initially people thought about, okay, if I put a magnetic field over and if I send a beam of neutral atoms or cesium atoms, I will get a simple blob over here, because that's what is expected. Like for example, there is a hole and I'm shooting a gun and there is a screen. So what I expect is the mean distribution will be something Gaussian if it is perfectly done. But to their surprise, they found out that instead of being a Gaussian, it's split into 2 directions. So they were very surprised, because there was nothing to be, like nothing, they actually just put a magnetic field to it. And the split was happening. So it was attributed that these particles which are coming, or the cesium atoms which are coming, they have an intrinsic spin to them. Like they are by themselves either spinning upwards or they're spinning downwards. Like they're either this way or they're spinning this way. And this state is inherently in a superposition state. Before it is measured, like we saw for photons also, before it is measured, it's in a superposition state. And that's why they got an equal distribution. So even using these schemes, we can generate QRNGs. Like this diagram represents that. So up to now, you should have been motivated. Like there are a lot of schemes we can use in quantum which can be used for QRNGs. Now, no special, because they had cesium atoms with them in the lab. They just use cesium. We can use rubidium also. In our lab, we use rubidium. So no, they had a lot of money. Come on, these are very old experiments. It's a neutral atom. Basically, it's a neutral atom. It's not meant to be like they do have some radiation signatures, but it's not meant to be radioactive. All they wanted to see is if the atom I am just shooting, it's like an electron gun, like CRT we have. No, we can use a CRT also here. That is not also a problem. Even electrons by themselves are either up spinning or down spinning when you use a CRT tube. Okay, having said that, now let's go into the more practical things, like how this laboratory research can translate into a product or a solution which can come into the market. Okay. Types of QRNGs, like I've said, trusted device QRNGs, semi-self-testing QRNGs, and self-testing QRNGs. Can someone by some knife thought tell me how can like trusted QRNGs be better than self-testing QRNGs? Some knife. Anyone, Diksha or Aniket, you may also try. So I'll just tell you, okay. Any process which needs user to be tested, and only after the user tested you get the output, it is slower, right? And when we talk about QRNGs, we talk about speeds in Gbps or maybe tens of Gbps. So trusted QRNGs, because they don't give any user testing facility, they are very fast. But these guys who give testing to the user, they're very slow. But they have an advantage that user, if they can question tomorrow, okay, I don't trust you, bro. What have you done? I don't know whatever. If your QRNG is an actual QRNG, they cannot question it here, but they can definitely question it here. So that's how different QRNGs are classified. And today the market is populated by trusted device QRNGs. Like the 80% market share is with these guys, but they are coming slowly in the market. Now, talking about the security, like I said, assumption is that the trust is in the quantum hardware provider for trusted QRNGs. For semi-self-testing, it's partial trust. You don't completely trust also, but you get some testability functionality also. And finally, self-testing, where the user gets completely independence. Like they can test it at their own will. Implementation, definitely, for trusted, it is easier because they are not giving anything to the user. Relatively difficult, and it is most complex. Certification, now any device we need, like FIPS certification we have, and a lot of different certifications we have, right? So for QRNGs also, this certification is usually provided by the vendor because you cannot test it, so you cannot certify it. Then they offer a higher confidence to the user, but again, dependent on the user validation. And they provide highest certification level to any user. Like I said, speed, very high speed, very slow speed. Like to talk about the speed, their random number generation is at bits per second, like 10 or 20 bits per second. And finally, the drawbacks, definitely. Now, let's talk about real things. So this is a chip-based QRNG, which is this small. It's a board, and this is just few millimeters smaller. This is a PCIe based. So you have seen like how the lab experiments we are talking about big photons going here and there. People have actually boiled down to so miniaturized architectures. And then again, they can be, based on form factors, they can be classified in multiple domains. Like can be chip-based QRNG, can be portable QRNGs, can be network appliance-based, can be quantum computing-based. Last for the best. Best is for at the last, okay? I'll tell you what exactly that is. Now this is taken from the ITU document. So they have released a standardization draft where they have said, okay, if you are designing a QRNG, you must follow this process. Otherwise, we don't take your QRNG for a QRNG. So again, the thing is very simple. If you have understood the examples I have said, it is going to be very easy. First, you start with quantum state preparation, which was my psi state or my superposition state. Then you do quantum state measurement, which was my beam splitter. Then after the measurement, you get some result, which is the data acquisition, or we get the raw data out of it. Now, what you are trying to monitor, it's source parameter monitoring. What it is, my state should be equally probable. Like my superposition state should be actually superposition. Like it should not be something alpha plus beta. What I desire is this state, right? I do not desire any other state, like for example, alpha plus beta. I don't want this. If my alpha and beta are not equal, I don't want them. So that is what your source parameter monitoring will do. If it is not, so you can actually define some threshold. If it is not passing the threshold, you say, no, prepare the state again and do it again. If everything is good up to here, once the raw data is acquired, it will do post processing. Now this part is little tricky because I have said, okay, I have generated the random numbers. Why do you need to post process it? You have the numbers, right? Why can I not directly use it? We will see it in the next slide. So hold for now. And finally is entropy verification, the most important parameter. Like we need to see how much entropy the source is about. And finally you get your output. Now talking about randomness test. So any random number which has come out of the system has to go through a certain test or certifications. So it can be classified in 3 different test classes. First is statistical test. So statistical test can be again of 3 subclasses, like test for uniformity. Like how, for example, out of 1 lakh bits, only 10,000 of our bits are uniform. Uniform means equally probable, but the next 10,000 is not. So it will fail the test. So it tests for the uniformity in the entire sequence. Then it tests for independence. For example, my first block was completely random. My next block is little less random. My third block is more lesser. It just falls down. So it will test that. And again, all of them are equally, like it will, all of the blocks are passing the test. So this test will find out whether this block is independent or the other blocks are independent on each other or not. So if they are dependent on the other blocks, then it is not random. So there are a lot of sequences or tests, different kind of statistical tests you can do. And there are test suits also. Like if you go and Google NIST SP822, you will get the test suits that they provide, a different test. Then you can do entropy based test also. Like you can do the minimum entropy estimation of the source. Like we understood that minimum entropy has to be maximum. Then you can do Shannon entropy also. And finally, you can do some quantum specific test also. Like in the numbers that you get, how do you know exactly if it is quantum or not? If it is a classical generated source, how do you differentiate it from it? So that part you can do with quantum specific test and validations. Now we talked about post-processing, right? A few minutes back. So post-processing helps us to, so like in this example, what I had a light source, I had a beam splitter, and then there was a measurement device. So this light source had to be powered up, right? It has to go, some electrical power has to be there to generate the light. For example, pen lasers, if we have battery cells on it. So it has to get some power. But these lasers that I'm talking, they run by plugging it into the real hardware. So there can be some hardware noise also which has come out, and that is not quantum. How do you know that that has not mixed up on the random sequence? Maybe the power has been fluctuating. That's why laser is like on and off and something is happening. So post-processing helps you to churn out the classical noise out of the system and keep only the quantum noise. So that's why post-processing is implemented. And there are different form of extractors or post-processing algorithms, we call it, which can be used to clear out any form of classical noise and only keep the quantum noise in the system. Which can be XOR-based extractors, von-Neumann extractors, Stavasian and Toeplitz. So all of them provide different level of security and different advantages which can be used. Like it's told about certification standards, any product or anything which comes out in the market has to go some certification. So these are some standard certifications which are existing today, on which you can certify whether your random numbers are actually random. Now let's talk about some advancements in QRNG. So this is one of the smallest QRNG in the market, which is just 5 centimeter, this small, and the width is around 2.5 centimeter. So everything that we have talked about, every ITU document or everything that we have seen comes and fits in this size. This is this small, the people have come out with this small size of QRNGs also. So anyone who says tomorrow that quantum hardware is very bulky, cannot be used, just show them these figures. Quantum hardware need not be so big. Even they are small, they can be useful. Definitely, computers are very big, but not all quantum hardware. These are some more examples for QRNGs in the market. This is a 19-inch rack system that is like the size of my mobile, and this is again PCI based. So I'll just skip through these slides. This is a USB based QRNG. This is very big. This fits in a data center. If you need a data center based QRNG, and this is for you. There can be a lot of things. And interestingly, there is a company called as ID Quantic. They have actually installed a QRNG chip on their Galaxy smartphones, which is the Samsung smartphone. So I happened to visit their stall, and this was the phone which had the chip on it. So they have actually shown that it's called as Galaxy Quantum Edition or something like that. So this is the chip which goes into this phone, Samsung Galaxy. And you can see like lot of classes of QRNGs. I don't know if it is visible from the last. Can anyone see the highest speed that have been achieved? Is it visible? No, right? So the highest speed is 2 Gbps, like 2 gigabits of random data you can get per second. Now, it's all a good story till now, right? It looks like QRNGs will win the market and they are the next big thing. But let's look into some challenges, some practical challenges that comes with quantum technologies inherently. First thing is hardwares are complex. The things that we have seen today is actually not so easy to design in the lab. So it's a complexity challenge is there. Next is scalability. Now, not every architecture can scale as good as the others. So scalability is also a challenge. Next, expensive. Expensive because the things we are using, you know, right? Quantum, like ma'am was asking me how costly it is going to be or implementing a algorithm on quantum computers. I say it's pretty much costly. Why? Because they need specialized environments, specialized systems on them. So they are not as like readily available. So they are expensive. Then there can be some side channel attacks on them also, which can reduce the security and can increase loopholes on it. Then some QRNGs have shown to take lot of power, and if we are using it for some space application, for example, if you want a QRNG deployed on a satellite, it will generate it will take lot of power. So that is something we won't want. Now, comparison between different QRNG designs, it can be like bulk optics based. For example, it's very bulky. We have seen different form factors, right? So it's just a differentiation between different form factors. Like it can be bulk optics based, it can be, sorry, chip based, it can be quantum computer based, which I haven't explained yet. And it can be something which has been hidden, but maybe, one of the other classes. Then we can like define them in different classifications also, like based on the speed, based on the cost, based on the data streaming rate, quantumness, how is the entropy, and multiple other things. Now comes the quantum computer based. So I'll just sip some water. So meanwhile, if you have any questions, you can ask. What we'll see next is how you can use a quantum computer to generate something which is very random. Yeah. Yeah. So there are yeah. From a quantum source, no, yeah, which is true. Which is true. I'll just go back to the slide once. This slide, right? So if it is generated from a quantum random source, then it will pass some certain test, Bell's inequality test. So Bell test is we'll see it in the lecture day after tomorrow. What is Bell's inequality test? But it is a classical signature which shows that it is not possible to be generated by any classical source. If it is quantum only, then this will be generated. No other way. So if your random number generators are proving that, okay, I'm doing a quantum phenomena, and if it is using entanglement, you can actually pass it through a Bell's inequality test.
Is it only for authorization or random number generations, more or less? Right? So when you are taking these and high fundale where you have data, then you have image type of securities, basic implementation
Remains same. Yeah, basic implementation will be same. Applications may be different. Yeah.
So in that scenario, why quantum? When we are looking at the quantum, what is the first application when we are trying to learn is quantum random number generator?
Yes.
That is
Yes.
the first thing what we
Yes.
are learning
Yes.
from learning perspective.
Yeah.
Why this has got that much importance?
Yeah, I'll tell you. So
Because
we are.
other when
Ha, ha, ha.
classical, when we are talking classical things,
Yeah.
not many things we have already seen.
Yes. Right.
Starting from random number generators to the highest
Mm-hmm.
right? But why quantum?
Quantum is, yeah. Yeah, I'll tell you. So I'll not tell you the entire story because that's setting my tone for tomorrow's lecture. I'll tell it tomorrow very nicely, but I'll tell you. We use AES encryption today, right? AES 128. That uses some key. That key has to be generated from a PRNG. We are directly doing it from a PRNG. But if that is not secure, if we can predict that key, then your entire AES encryption is of waste. So to create a pure random key, we need a random number generator. So it found a lot of uh, highlight when the case of cybersecurity came in picture. In cybersecurity, we need a complete random source for doing lot of things. We will see tomorrow in quantum communications lecture also that to do something like for all the threats that is coming out due to quantum computing, we need something which is completely random. That is one aspect, but hold on, for tomorrow we have the entire 1 hour session for that. All right.
పొద్దున వస్తాను
Okay, so let's start. Let's resume. So let me ask you all, why do you think you will need a quantum computer? Any idea? Are you going to use it for doing faster Excel sheets or faster addition subtraction tomorrow? No, right? So like we have seen an evolution. Initially it was just CPU, then came GPUs, which are good for gaming and other application where you need lot of screening or other things. Then came TPUs, tensor processing units. Then came data processing unit, or which comes in DPUs, called as DPUs. Then came a new revolution of QPUs. So it's a new class meant for certain applications, which is not otherwise possible. And in the first talk today, we have seen that there are some optimization problems which quantum is very good at. And there are some other problems also which quantum, like factorization problem, which is quantum very good at, like finding images, very good. So having said that, now quantum computers, if they are actually doing something quantum, there was a proposition which came up in 1996 by Seth Lloyd. He said that a quantum computer, if it is universal in nature, it can simulate any quantum experiment which is happening. Anything, it can do anything. Even if it is not an abstraction, you need to understand it, okay? It's not an abstraction or a simulation I'm talking about. A quantum computer which is designed by qubits or quantum entities can replicate any quantum experiment which is happening. Anything. Whatever I've talked about this thing in the lab that we are trying to do, this computer, if it is universal, it should be able to replicate that on its system itself. And that is not simulation. You should understand that. Simulation is like it's an abstraction of whatever we are trying to answer, right? But if it is actually quantum, you can actually demand that system to behave in a certain way that your actual physical experiment is replicated. Having said that, that is something we can actually use. So again, this is something we work on. So what we do is this experiment which was done here, like a photon which was coming in and there was a beam splitter, if you remember, then light went on this direction and this direction. So we try to replicate that experiment on quantum computers. If we are able to do that, then the output that we get is completely random, right? Agreed? How we do that, it's a physics thing again, but I will not go into that. It's like the Schrodinger equation comes in and all these physics things come. But let's try to understand get the feel of it, what we're trying to talk today. So there is a process of how we try to do it. First there is a experiment. Okay, I've done it in the lab. What my next goal is, I want to take this experiment, do it on a quantum computer. For example, Diksha was showing some of the quantum gates to do something, right? So what you know up to now is there are qubits, there are gates, and then everything is your logic. Whatever you do on that, you will be able to generate some output of it. So I'm trying to map this now. This is my physical experiment which I did in my lab, and there is my quantum computer giving me all these gates and all the qubits. I want to map this experiment. So what I'll do, I'll first note something in physics we call this Hamiltonian of the system. That is called as Hamiltonian mapping. After this Hamiltonian mapping, I'll be able to map that exact experiment on the quantum computer. How? By using gates. So gates have a mathematical structure to it. And when we write Hamiltonian, they also have a mathematical structure to it. All I need to do is I need to just bridge a correlation. I need to tell the system, okay, apply these gates, and this combination of gates or your circuit is equivalent to my experiment. That is all I need to do. And that's what we will do also. The moment we do that, we, like from the physical model, we directly go into the hardware, which is the quantum hardware. And finally, we get this, we do certain error correction and other methods to get to a good result. This is a pictorial representation. This was my physical model, which was my beam splitter and whatever things we have done. This is the mapping where we do poly-Hamiltonian mapping. And finally, we do a gate decomposition, which is like representing this Hamiltonian on the gate language directly. Again, this is how it looks. Simple experiment. And this is with the lot of gates and physical qubit blocks, you will be able to generate the same string. Now, if it is actually, okay, I think I can skip some of these slides. Let's go to something which is interesting. These are like signatures that you can see. Like there are physics-based experiments which you can do. I was talking about, ma'am was asking about some quantum tests, right? So these are some of the quantum tests we can do and see things. But what is interesting is here. So this is a random sequence of zeros and one. So this is generated by a source or an algorithm which is trying to mimic a physical experiment, and you see how random it is. There is no pattern. This is done by a simple Hadamard gate. Can someone tell why the Hadamard gate has a pattern to it? Hadamard, you know, right? It's like 0 and 1. 0 plus 1 by root 2. Can anyone guess why is there a pattern to it? Any answer? Hadamard is supposed to do 0 and 1, right? Superposition. And if I just measure it, I should be getting 0 and 1, right? But I'm not getting that. If it was true, then it should have been completely random. But why am I getting a pattern to it? Because the gates are noisy. Okay. Even if it is saying that I'm doing it 50-50, it's not actually doing it. And that is the difference you will get in your results also when you go on the real IBM hardware. In simulator, you saw 0.5 probability. The moment you go on the hardware, noises will come up and your data will be biased to one side. That is a physical experiment to see it. And again, these are like how we can use certain multiple QRNGs. But again, I think we already covered, so the main thing. Now, the question may come up like, how do we use something like a quantum computer-based QRNG on real service? Like, how can I get those numbers in my phone? So we actually need to do on a secure tunnel. Like we have to develop. So these are more of like industry level designs that I'm talking about. Okay, we have already covered with the physics and the basic part. This is more like how do we actually take that thing and bring it to the market, or how do we do that translation. So we generate the random numbers, then we have a secure vault where we'll be storing it, and there will be quantum safe channels which are generated by post quantum cryptography. Using that, we'll be able to do it with multiple clients. So there are different mechanisms, standard mechanisms also, and getting standard mechanisms also, because new standards are coming up which are taking into account quantum practices. And these are some of the parameters of whatever we found with our design. Like it can go up to some Mbps speed. It passes some test, quantum as well as the standard statistical test. And it can help you with, like you can choose multiple hardwares and different things. So there is another company also, Honeywell. So Honeywell is very popular with their connectors. Like whoever has like those MacBook connectors, they have those Honeywell connectors, right? But not just that. So Honeywell is doing some quantum, really good some quantum stuff also. So even they have certain similar design where they're generating quantum random numbers from their H1 processor, H2 quantum computers that they have, and then providing that as a service. So if tomorrow you need quantum random numbers, you can just register to their profile and they can provide you that. So this is how like quantum computers are not just meant for computing. If it is universal in nature, it can do a lot of things. With QRNG, it is just one application. And we have a lot of other applications also. In finance, we do financial modeling, we do Monte Carlo simulations, we do portfolio optimization. Like the list goes on, goes on. To close on with the final slide, with QRNGs, there can be a lot of applications that we can see today. Like optimal route, it can be used for routing protocols. When we do Dijkstra or something, we need some random sequences to predict something. Then in risk management, option pricing, financial modeling of systems, then online gaming, lotteries, cryptography is the main thing, secure OTPs, and many other things. Okay, having said that, that's all. So if you have questions, thank you. Yeah, sure, ma'am, please.
This was all basic because we are all laypersons, so excuse me for asking this.
Yeah, please, ma'am, please.
We wanted to learn. Actually, when we are trying to generate the random numbers, it's ultimately has to be transferred to any of the classic machines.
Yes,
So
yes,
we
definitely.
basically use all this.
Yeah.
All these exercise, what we are doing to generate the random numbers, fine, I accept that it is being generated by quantum, but has to be converted into classical
Yeah.
format, which is to be again transferred to the machines,
Yes.
whatever we are using.
Yes.
Now, how could that impact the actual vision what we are looking at?
Yeah, I'll tell you. So, okay, that's a very good question. I'll just reiterate that. So, we have talked about quantum processes, which are like superposition state or something like that, right? But at the end, we are talking with classical systems or using it in our traditional systems. So, how does that translate, if I'm right, ma'am? So, the moment we say random numbers, which is 0 and 1, we already came down from the quantum to the classical. So superposition was before it was measured. The moment it is measured, it is just random string of 0 and 1. That is my classical data. So whenever I want to input that data into a classical system, I'll take that bit string, not the superposition. I'll take that bit string which has been generated, the 0 and 1 random sequence, and I'll use it on my systems. So that translation is my quantum process, my classical bit string output, or the bit string output, and that goes into the traditional system. This is the roadmap. Yeah.
So, what we really get the benefit out of what is being required.
Yeah. So the problem came up when the predictability of those random numbers was there. Like 0 and 1, for example, it is 0, 1, 0, 1, 0, 1. Then it is 0, 0, 0 4 times and 1, 1, 1 4
Is
times.
that now the random number that is being generated by whatever is being done is not predictable?
No, it's not. That's what we are trying to secure. We have learned about entropy bounds. So entropy gives you information about how much useful information you can get out of the system. Then we have this statistical test. Now, yeah.
Entropy minus P log P.
Yes,
Everything
definitely.
classical also.
Yes, right.
Can't we do that actually?
We-
The same
Yeah. So there are two classes I've said, right? PRNGs and TRNGs. So PRNGs, they can actually show good entropy and everything. But the problem is they are seed based. The moment I know the seed, I know the output. Very big flaw. The next resort which came was true random number generators, which is said, okay, I will not rely on algorithms, but let my hardware do some. Like this laptop, it is generating some hit signatures. I'll take that.
So I know the same thing.
Ah.
I have a mechanism where which I randomly generate the
Yeah. But here in this second class, the problem is you cannot define the entropy. Right. So the trade-off you are seeing, the first one was very good. Entropy also good. Randomness is also good. But the moment you know the seed, entire thing is gone. Second one is it's not algorithm based. You don't have a seed, but entropy is not definable. With quantum, you get both the advantages. Yeah. Okay. Any other questions, or we can? Okay. I think that's it. Right.
Sir, any other questions?
Yeah. Sure. So how do I do that? Let me give you my pen drive. Wait.
Let me thank our speakers, Ms. Deeksha Sharma and Mr. Riktim Baumik, for sharing their knowledge and enlightening us in the field of quantum. And thank you so much for conducting an excellent hands-on session. And the way you simplified complex concepts and guided us has helped us. So, let me call upon Professor C.V. Gururao sir, Uma Devi madam, Shiva Prasad sir, Anuradha madam, to felicitate our speaker, Ms. Deeksha Sharma. Now I call upon Mr. Riktim Baumik. I request Praveena madam, Nagalakshmi madam to join the felicitation. And Rajeshri madam too. Rajeshri madam. Srinivaslu sir also. I request Srinivaslu sir from chemical department to please join the honoring. Thank you. Thank you, one and all. Sir, I hope everyone has signed in the attendance sheet.